Hello, this is Sean Hargrove, and this is a walkthrough on how to uh, simulate a flow over a flat plate in ANS Fluent. So what you want to do is drag a fluid flow over onto your workbench, and we're going to go into geometry. I'm going to wait for this to load up, and we're just going to go into sketching. We're going to sketch a rectangle, and then we're going to specify the dimensions. I want the length to be 1 meter, and we're going to be using this this flow to look at like the boundary layer and skin friction and stuff like that, but most importantly the boundary layer. You want to make the height comparable, your max height comparable to your boundary layer height. I think the boundary layer max height for the simulation I'm about to do is like 13 millimeters, so I'm gonna make the max height 35 millimeters. And then we're going to go back into, gonna create a, no, not create, where is it? Yeah, concept, surface from sketches. And we're gonna grab this box select, grab this, apply this, and generate. And now we have this. And that's all you need to do in the geometry, so we can close out of here. We're going to go into mesh. Going to change the orientation. And the first thing I like to do is go over here, click edges, and name my edges. It makes it easier to differentiate from them later. I'm going to call this one inlet. This one could be outlet. Call this one a plate. And then the top is not going to be a plate. We'll call this far edge. And then next, we're going to want to create some meshes. First, we're going to create the top and bottom mesh. If you have the edge, click, and if you can control click, you can select both of them. Right click on mesh, and then we're going to insert a sizing mesh. We're going to change it from element size to number of divisions. I make the number of divisions 100. Probably could do a little bit more. We'll do no, 100 is probably fine. And we're gonna switch off capture curvature and set the behavior to hard. And then we'll generate this mesh. And then we have probably the most important part. One of the most important parts about generating the mesh is we're gonna select this and insert another sizing mesh for this size. Make this number of divisions. I think I made this maybe 50 divisions. But if again we go capture curvature, we set this to hard, but we're going to be generating a mesh to see the boundary layer, which is going to be down here on this plate, which means you want most of the nodes to be down by the end of the plate, and right now it's just evenly dispersed, but there's not going to be much changing up here, so we're wasting processing power having most of them up here. I mean, you could make a bunch of divisions and then you get it, but an easier way is if you go over here and change the bias type. These lines kind of give you like an idea of how the bias is going to go. So this one is like, you'll see like there's a very few near the top, and then the bottom there's a bunch. So if we click this one, make it a bias factory of, let's say 70. Actually, I clicked the wrong one. We want this one. No, did I click the wrong one? No, this is the right one. You can see we have a few big ones up here, but as it gets to the bottom, it gets very small and fine. Maybe we can even do a bit more divisions, do 60 divisions. Maybe a bias factor of 80. And then we can generate that sizing. And then we'll go to the right side and do something similar. Select edge again, this one, insert a sizing. Instead of element side, we need number of divisions, 60 divisions. We want this to prioritize our mesh that we're going to define. Change the bias type to this first one and make it a bias factor of 80 like the other side. And I think that should be good, so we should be able to generate it. And then if we go into mesh, you can see they're about mirrored both sides. Now we want to clean it up a bit because now we've got like good coverage where the boundary layer would be at the edges but not in the middle. So if you go into here, then we insert a face meshing. This should help clean it up. Select this geometry, click apply. It has this selected, and then just generate this. And after it finishes, if you click mesh, you should see that it's nice and uniform, but most importantly, the bottom half, the bottom part of it, has a very fine mesh. If you zoom in, you'll see that as it gets to the bottom, mesh is very fine. Might be worth making the top and bottom plates spacing for the sizing. Maybe make it a bit bigger, because it should change a lot, but this is probably fine. That should be about it for the mesh, so we can close out of this now. Well, it's closed. I'm going to open this up. You want to right click on this and update it so that it has the mesh with the geometry. Setup for the setup. Alright, after you right click this and update it, double click on setup. Start the launcher. Perfect. Okay, is it in, actually I don't think it's in general. Yeah, here it is. Go into models, and then we're gonna go into viscous, make sure that this is laminar, because we're looking at laminar flow. It's the only thing we need in models. We go into materials, into fluids, and change the property of air to whatever you have specified. I've got 1.2 kilograms per meter cubed and 1.8 times 10 to the negative 5 for viscosity. Click change and create. Let me just go back and double check that my thing's saved. And then we're going to want to not cell boundaries. So do we want to go to boundary conditions? Inlet should be a velocity inlet, and change it to whatever velocity you have for your simulation. I'm gonna put it at 2, apply that and close. Outlet is a pressure one, and you shouldn't have to change anything in here. Just make sure that the inlet and outlet pressure, gauge pressure, are the same, so that there's no like forces due to pressure difference at the outlet. Everything should be good, so we'll just close out of this. The important thing that you want to do is we don't want the far edge to act as a wall, so if we right click this and click type, make this a symmetry, and you shouldn't have to just see this is a symmetry. Close this. You don't have to change anything in here. And the wall bottom plate, you just want to make sure that it's no slip, stationary, which it should be by default. And so I think this is good. You can double check for your reference from the inlet. See that it's saved. That's all good. Okay, after you check your reference frame, your reference values, you want to go over to monitors, go to residuals. This basically dictates the accuracy of the equations that's going to run. So you can bump these up a bit if you need yours to be more or less accurate. It probably won't change too much because it's a simple simulation, but for other things you might need to increase your accuracy. But after that, you can double click initialize and have it initialize your thing. It shouldn't take too long. And then after that, you can double click on run calculations. You want to do your number of iterations. I'll do 200 iterations. This one's pretty quick, so you could probably do more, but I don't want to wait for too long. So we're going to do 200 iterations. We're going to calculate. You have your chart that tells you your continuity and whatnot. You can see how it goes. It's kind of a good progress bar while you're waiting, but that's done. I did 200 very fast. The last thing that we want to do is before you go to your solutions, you can check some solutions in this window. If we go into, where is it? For one, you can go to plots and double click XY plot. And if we do wall fluxes, and not shear stress, but skin friction coefficient for the plate, and we're gonna, or actually not for the plate, the interior surface body. Yeah, and then we click save and plot. Close out this. You can get your plot here, so you can see it. But if you need the values, if we go back into this, double click this, and just click write to file, it'll write it as an XY file to save it. And then if you can go into Excel or a program like Excel, you should be able to open up the XY file and it should export your values. That's how you get your skin friction. If you also go down here to reports and double click forces, you can do forces onto the plate and print this out, and it'll tell you the forces, your pressure forces and your viscous forces, which the only viscous force here is going to be your skin. This would be skin friction, or your viscous forces is like your pressure force, but this is like flows going parallel, so it's just going to be skin friction basically. So this is your total force, but this is probably what you're going to want more, your coefficient, your skin friction coefficient. So you have this down here to compare with your theoretical values. After that, you can close out of this. Yeah, that's good. Close out of that. And you can see we got the check marks for the other things. Once you've gotten your skin friction and drag coefficient numbers, you can double click onto results. We're going to do this like this again, and now we can insert some contour and vector map. Contour 1, all domains, location should be symmetry 2. It's going to be pressure. I don't need to change this. Number of contours, make it a high number. We're going to change the legend because this is very in the way. Make this horizontal. And we'll just do, that's good. I don't need to show the units. Apply that. So this is your pressure contour map. Then we can add vectors as well. All domains, it's going to be symmetry 2 again. Should be velocity, which it already is. You can apply this. and you can hide the contour if you want to look at your velocity vectors. Yeah, okay, and I'll hide this because that one looks ugly to look at. Then we can also plot the velocity and the wall shear. So to do that, we're going to make a couple lines. Line 1, I'm going to have at 35 centimeters. Make this near the top, which is 0.035. And make sure you have a bunch of samples, so you can get an accurate reading. And then we're going to make one more line at 75. A bunch of samples. Okay, perfect. So these which are for, we can get an idea of how the velocity looks at these points. We're going to make a quick chart. I'll call this velocity. And with the series, sure. We'll call this 35 centimeters. And this would be line 1. We'll add another series, which will be 75 centimeters. And we'll make this line 2. And then we can make the x-axis, we'll make it velocity u, your x velocity. Yeah, and then the y variable will be how high up it is. And if we apply this, you can see the velocity as it hits kind of the edge. And you can also use this to kind of get an idea of how thick your boundary layer is at a certain point. If you look at the where the line kind of gets close to max velocity, so probably like around here or around here, you can find the y value and you can get a good estimate as to how thick your boundary layer is. So that's your velocity chart. We can make the wall shear chart. Oh, we need to make one more line before we do that. Where did my line go? Line 3. Oh, I'm here. I'm not looking. Let's go back to the 3D viewer so I can see. We'll make this from 0 to 1 is good. At y equals 0, 100. This should make a line basically at the wall. Maybe we make it not exactly at the extremes, so it doesn't give us very wonky values. Let's just kind of make it close to the, that actually might be, that's way too much. I've added a couple more zeros. Maybe like that. Okay. That's probably good. Just so we don't get super extremes, but it probably doesn't change too much. And now we can make the chart. Go to chart 2. This will be wall shear. We'll make this series line 3. The x-axis should be wall shear, and the y-axis should be x, I guess. Yeah. Actually, maybe we should make this one x and then y wall shear. That might make more sense. it would just flip it. But this is the plot of your wall shear as you go from left to right. And those is basically how you get all of your values to check with your theoretical ones. If you need, like for velocity, if you want to test your theoretical boundary layer thickness over what Fluent gives you, on any of these charts, like this one or this one, you can go down here and click export, which is kind of like the XY chart that we exported earlier for skin friction, except this one just exports it straight as uh, an Excel file, so you don't need to import it into Excel or anything like that. You can just export this and then double click the file. You'll get your X and Y columns, and then you can more easily interpret the data. But that's about it. It's a pretty simple project, but I guess it is a very simple shape. So